Extracting oil and gas miles offshore means pushing engineering into one of the most hostile environments on Earth, the deep water abyss. Subsea pipelines transport a multi-phase fluid, a volatile, complex mixture of crude oil, natural gas, and produced water pumped directly from the reservoir. As this mixture leaves the wellhead and enters the seabed infrastructure, it slams into a harsh physical reality. At these depths, the surrounding seawater temperature hovers near 2 degrees Celsius, or 36 degrees Fahrenheit. Simultaneously, the fluid is subjected to immense physical forces. It operates under internal reservoir pressures that frequently exceed 1,500 pounds per square inch, while fighting the crushing hydrostatic weight of the ocean above. Keeping this raw, volatile fluid moving continuously across miles of freezing, highly pressurized seafloor falls to a highly specialized engineering discipline known as flow assurance. Drilling the well and tapping the reservoir is only half the process. Transporting that raw, multi-phase flow through a near-freezing environment without catastrophic blockages dictates the survival of the asset. The moment the multi-phase fluid leaves the heat of the reservoir, the sudden drop in temperature and pressure alters its physiochemical properties. Engineers attempt to trap the initial heat using thick foam insulation around the pipes, or by burying the flow lines directly into the seabed. However, over long subsea tieback distances spanning several miles, passive hardware solutions are insufficient to prevent the fluid from solidifying. Maintaining continuous subsea production mandates active, precise chemical intervention to neutralize specific physical threats. Flow assurance engineers must continuously monitor and combat 4 primary categories of pipeline failure: hydrates, wax and asphaltene buildup, scale formation, and corrosion. Each of these threats requires the continuous or carefully timed batch injection of highly specific chemical agents directly into the well stream. Deepwater subsea extraction is an exercise in applied chemical engineering. Operators actively alter the chemistry of the fluid in real time to bypass the thermodynamic limits of the ocean floor. The most immediate risk to a subsea pipeline is the formation of gas hydrates. Under high pressure and low temperatures, light hydrocarbons like methane and ethane bind with produced water to form solid, ice-like crystalline plugs. During feed, engineers use this phase envelope mathematical map to predict solid plug formation. The black line is the PT profile, mapping fluid cooling. The failure point is this intersection. When the profile crosses the orange hydrate line, fluid freezes solid, halting production. This risk spikes across subsea chokes. Due to the Joule-Thomson effect, a rapid pressure drop across a choke valve causes an immediate, severe crash in fluid temperature, accelerating hydrate formation. To counter this, operators pump in thermodynamic inhibitors, primarily methanol or monoethylene glycol, commonly referred to as MEG. Functioning like antifreeze, these chemicals interact heavily with the water molecules. Injecting MEG alters the phase envelope data. It shifts the hydrate formation boundary to the left, moving it safely out of the path of the black PT profile line. Thermodynamic inhibition effectively rewrites the fluid's physical limits, suppressing the hydrate formation point so that solid plugs cannot exist in the deepwater environment. While hydrates involve gases and water, the oil phase of the fluid carries its own kinetic threats, heavy hydrocarbon chains. Every crude oil has a specific cloud point. This is the temperature threshold where long-chain paraffins dissolved in the oil begin to crystallize into solid wax. As the pipeline loses heat to the surrounding seawater, wax precipitates out of the fluid and adheres to the cold inner walls of the steel pipeline. Sudden pressure drops can trigger a similar precipitation event for complex aromatic compounds known as asphaltenes. The physical consequence of wax and asphaltene buildup is identical. They slowly choke the pipe, restricting its internal diameter. This generates massive backpressure until the flow stops. To solve this, operators use kinetic inhibitors. Unlike thermodynamic chemicals pumped in massive quantities, kinetic inhibitors are injected in small, targeted doses. They act as crystal modifiers, binding directly to wax molecules to prevent interlocking or sticking to the wall, flushing safely away. When heating a pipeline or pumping massive volumes of thermodynamic inhibitors is no longer economical, kinetic inhibitors buy engineers the time and flow capacity needed to keep the system running. Beyond the hydrocarbons, engineers must manage the produced water pulled from the reservoir, which carries its own unique dissolved hazards. As the produced water travels through the subsea system, sharp shifts in pressure and temperature alter its chemical solubility, forcing dissolved minerals to drop out of solution. These precipitated minerals, specifically calcium carbonate and barium sulfate, crystallize onto the pipeline walls, creating rock-hard blockages known as scale. Scale inhibitors are injected to chemically disrupt the microscopic nucleation process, stopping the minerals from forming crystalline structures before they can build up. Water also poses a structural threat. Natural gases like carbon dioxide and hydrogen sulfide frequently dissolve into the produced water, creating a highly acidic environment inside the pipe. This initiates sweet corrosion from CO2 and sour corrosion from H2S, chemical reactions that eat away the steel of the pipeline from the inside out. The defense here relies on internal corrosion inhibitors, specifically filming amines. These molecules operate by linking together along the inner surface of the pipe, creating a microscopic, solid protective coating to block acid contact with the steel. Managing produced water is a delicate chemical balancing act, preventing minerals from building up while simultaneously stopping acids from eating the pipe away. This presents a logistical challenge. How do operators deliver highly specific chemical cocktails to a wellhead thousands of feet underwater and miles away? The solution is the Subsea distribution system, which acts as the circulatory system of the entire subsea architecture. The primary delivery vehicle for these fluids is the integrated umbilical. Inside a single umbilical, chemical injection conduits are heavily armored and bundled alongside electrical power conductors, hydraulic lines, and fiber optic communication cables. Looking at a field architecture schematic, umbilical lines transport chemicals from storage tanks on the surface host facility down through the water column. Once at the seafloor, an umbilical termination assembly routes these services across the field to specific subsea manifolds and wellhead trees. The chemicals are injected directly into the subsea hardware, mixing with the raw multi-phase fluid exactly at the source of the pressure drop. Determining the precise chemical types and injection volumes required to protect these lines is the most critical output of the multi-phase flow simulations run during the initial front-end engineering design stage. Ultimately, flow assurance requires balancing the massive capital cost of subsea hardware against the continuous expense of chemical injection. Correct chemical selection ensures that even under extreme pressures and near-freezing temperatures, the well stream remains fluid, sustaining the asset over decades of operation.